Okay, so in the last class, we started talking about different machine learning algorithms. In fact, we are into classification learning, and what we have done so far is uh, just to understand in general what is machine learning, and uh, basically machine learning is using data as experience for the machine, for the model, and training that data to learn a target function that can be used to predict values. And the scope of this, or the main aim of this, is that data is a representation of the underlying system. And if we have enough data, can we have enough understanding of the underlying system? And can we capture that understanding of the underlying system into a model? And if we understand the system that is there beneath the data, then we can use that system to predict for unseen cases. That's the main aim of maybe machine learning, to which we saw different examples of supervised learning. We said supervised and unsupervised is divided in. Within supervised, we are looking into classification. We saw the phases of training and validation and testing. We looked at one basic machine learning classifier, KNN, which the idea is if you are similar to your neighbors, then you are one of them. So we saw how to calculate distance. We implemented KNN from scratch. Uh, we talked about certain metrics that can help us identify if our model is good or not. So we talked about accuracy, precision, recall so far. We saw how to evaluate precision and recall. We saw different metrics like F1 score, F beta score, which are basically combinations of precision and recall. F beta is where we can choose importance of do we want to give precision more importance or recall more importance, and so on. We also saw uh, threefold set of data that divides into training, validation, and test. We saw this part where we talk about k-fold validation or cross validation. And finally, in last class, we talked about naive Bayes, and we saw how naive Bayes uses Bayes theorem and how we can use Bayes theorem to evaluate individual probabilities that help us to evaluate the net probability. Okay, so this is where we stopped last time. Do you have any questions before we go ahead? Okay. So in this class, we'll talk about something called as decision tree classifier, which is again another major or a very common or famous classifier that is used quite often, and it is very simple and it's very powerful. Okay, so here this classifier, it starts with the idea of creating a tree structure, and it uses that tree structure to represent uh, known data. And once we have an idea of the representation of the known data, we can use that same tree to predict for unknown data. So the idea is it breaks down the data set into smaller and smaller pure subsets while the tree is incrementally developed. Okay. So pure subsets means we are looking at groups of examples where all the class is same. Okay, all the target variables are same. So if we are talking about 1000 different rows, and those 1000 different rows can have different classes, they're looking for dividing into groups where within a small subset or within a small group, all the classes are same. All the classes are similar. Okay, when we go to the example, it will make some more sense. Here, the tree structure is basically having nodes. Okay, so you start with something like a root node, and then you say, okay, let me divide that into multiple nodes depending upon what feature it is. And each node can further be divided into multiple nodes depending upon how many values it takes and so on. And finally, if the node is having just one element, or if it cannot be divided further, then we call it a leaf node. Okay, we call it a leaf node. So either you can have a leaf node or a decision node. A leaf node is where the tree ends for that particular path, and a decision node is where we take a decision. Okay, we take a decision in terms of do we go left or do we go right, and so on, depending upon the situation. Decision trees can handle both categorical and numerical features. Let's look at an example which will try to make some sense into what we're talking. So here on the left we have the data, and here we have a tree structure that represents this data. So this data is very simple. And okay, just one second. Okay, so I have left out this column, which is from the old data. So just ignore this column. We have three features and one target variable. Hopefully we can ignore this. Okay. So we have three features like outlook, temperature, and windy. That basically all three talk about the weather condition in the present day. And we are trying to predict this fourth variable, which is play golf. So based on what is the outlook, what is the temperature, and what is the wind conditions, we decide that we will be playing golf or not. Okay, very simple made up data. And here outlook can take three values, either rainy, overcast, or sunny. Temperature can take three values, hot, mild, and cool. Windy takes two values, high and normal. Play golf is basically either we go or we don't go. So to represent this data, we are creating a tree structure like this. Okay? So which says that we'll first check for the outlook. If the outlook is sunny, then next we'll check if it is windy or not. If it is windy, if windy is true, then we will not play golf. If windy is false, we will play golf. Similarly, instead of sunny, if the outlook was overcast, then we'll directly go and play golf. In third case, when the outlook is rainy, we'll check for humidity. If humidity is normal, we'll play golf. If humidity is high, we'll not play golf. Okay. So let's look at some data and if this matches rightly or not. So if you're looking at this first one, we're looking for outlook rainy. So we follow this path. Then we look for uh, humidity. So here humidity is missing, right? Okay. So this is humidity. This is okay. I think I understand what's happening here. The labels are wrong. So let's rewrite the labels. Outlook is fine. Temperature. It's nothing like temperature. Mhm. Uh, Wait a second. I'll open my base notebook. Just give me a minute. Okay. So this here is humidity. This here is windy. This here is okay. So let's look at again. Let's try looking at first row. So first row, we look at outlook. Outlook is rainy, so we follow this path. Then we check for humidity. Humidity is high, so we go for this path. And we decide that we will not play golf. Okay, let's look at something else. Let's go for row 6. So sunny, and then windy is true, and we say not play golf. Okay, does this make sense? Okay, so what we have done is from this table we have generated a tree structure, and that tree structure represents to us every scenario here. Okay, so it represents to us all scenarios, and uh, based on this structure, based on this tree now, if someone tells me the given conditions, we can very well predict if we should say yes or no. Okay, so this is how the decision tree classifier would work out. Okay, so at this point, some very logical questions that should come to your mind is, how do I create this tree, right?
No, Elijah.
Okay.
This tree is created with the table which we have. If something comes outside this tree, like
Mhm.
uh, outlook sunny and option which is not there, our tree won't be able to predict, right?
What you're saying is, if the can
If
you
the
repeat that?
condition is coming outside, it means it is not in this table.
So you're saying instead of rainy, overcast, and sunny, if I get some new data,
Yeah.
then this tree will not be able to predict, right?
Yes.
Which is fine, because you see, the whole game about machine learning supervised is our testing environment should be similar to our training environment. Okay, so if your training data does not capture something, your model will never be able to learn it. Make sense?
Yeah.
Okay. So we are ensuring that if that is not true, then no supervised learning algorithm will work. Okay. So testing and training environment should be similar, and yeah, that's it. Okay.
Yeah.
The more interesting question is, if I have this data, why did I go for Outlook as the first option? And after Outlook, when I got sunny, why do I choose windy here? Why do I not choose humidity or temperature? Make sense? Can you probably try to guess how we would go about and create a table, like create a tree structure out of the table? Or what could be the factors which are important, or we should think that they're important to be able to create this tree? Any ideas?
No.
Outlook is the most important for the decision,
Mm-hmm.
and taken that as the base of the base. And next, depending upon the temperature, whether hot or mild or cool, that is of less importance when compared with windy.
So my question is, how do we decide if Outlook is the most important?
No.
Okay, okay, that's fine. So you said rightly, we have to choose which feature is most important, and based on, so the most important feature would be based on a certain criteria. Okay, so if you look at starting, we talked about something called as pure subsets or not. Okay, So it breaks down data into smaller and smaller pure subsets. So whichever feature out of this helps me to break down into pure subsets would be the most important feature. Pure subsets are subsets where all of the data points look like same. All of the data points have the same class at the same target variable. So for this, we use a term called as entropy. Okay, have you heard of entropy before?
Yes, enthalpy, entropy, and all we heard long
Yes,
back.
excellent. So entropy we must have studied in thermodynamics.
Yeah.
And do you know what entropy stands for? What does it mean?
Too sorry.
Okay, yeah. Same here. When the first time it was discussed in thermodynamics, I did not understand. But I remembered some thing. It says that the entropy of a system keeps on increasing. Okay, or the chaos of a system keeps on increasing. Entropy is basically a measure of chaos. Chaos means it's a measure of if my system is homogeneous or not. Okay, so entropy basically tells me if all the values in that set are same or not. If all the values are same, my entropy will be 0. If all the values are not same, or depending upon the chaos of the system, my entropy will be higher. Okay. So here we have some sense of that. If we partition into subsets, we have to partition into subsets which are homogeneous subsets. Homogeneous means all values are same. Okay. So we use for decision trees, we use an algorithm called as ID3. I don't know what ID3 stands for, but I know how it works. So I think I should find out what is the full form of ID3. So, but the ID3 algorithm, it uses something called as entropy to calculate the homogeneity. So here I have a graph which shows the entropy of a system. If all my values are 0, my entropy is represented by this blue point here, which is saying my entropy is 0. If all my values are 1, still my entropy is 0. If I have a probability of 50-50, okay, that is half of my values are zeros and half of my values are ones, that is my net average is 0.5, then the entropy is the highest. Okay, and depending again upon how much I have 0 values, how much I have 1 values, I'll have different entropies in my system. The formula that helps us to get this curve or helps us to divide into entropy is something like this. Okay, so it says if I have two sets, uh, P and Q, then minus probability of P, okay, minus probability of P. Probability of P just saying how many of the total values, how many are belonging to this one set. Okay, so minus the probability of that number and multiplied by log to the base 2 of the same number. And we'll go with as many sets we have. So if I have two sets, zeros and ones, then I'll say probability of being a 0 into log 2 of probability of being a 0 minus probability of being a 1 into log 2 of probability of being a 1. If I had multiple classes, so if I had classes like 0, 1, 2, 3, 4, 5, then I will take each of the numbers, probability of 0, probability of 1, probability of 2, probability of 3, and so on. I'll add all of those values, and that gives me the entropy of my system. Okay. So entropy is just a measure of homogeneity. More homogeneous, lesser the value, closer to 0. Less homogeneous means more mixed, then higher the value, like 1. Okay. So for creating a decision tree, we will use entropy, and there are two kinds of entropies that we want to calculate. Okay. So to build a decision tree, two types of entropies that we want to calculate. The first type of entropy is called as entropy of the target. The second is entropy of the target with attribute. Okay. So here our target is play golf, and these are our 4 attributes: outlook, temperature, humidity, and venting. So two kinds of entropies. One is just entropy of the target, entropy of play golf, and second is entropy of target along with feature attribute. So entropy of playing golf with respect to outlook, entropy of playing golf with respect to humidity, and so on. Okay. So in our first case, we are trying to find what is the entropy of the target. Okay. So my target is play golf. I have 14 examples here. Out of 14 examples, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 yeses and then 5 no's. Okay, 1, 2, 3, 4, 5. 9 yeses and 5 no's. So we say, okay, my entropy of the target is something like this. I have play golf, which has two values, yes and no. Yes is having 9 samples, no is having 5 samples. So my entropy will be evaluated by something like this. I go and do the summation of C's, okay, of I over C's. What is C? C is the number of classes that are there for this target variable. So here playing golf has two values. So it will go from 1 till 2, where we'll have minus probability of the first class, log 2, log to the base 2 first class, minus probability of the second class, log to the base 2 second class. Okay. So we're calculating entropy of playing golf, which says basically calculate the entropy of 9 and 5. So 9 and 5, if we convert that into probabilities, that becomes 0.64 and 0.36. 0.64 as basically 9 by 14 and then 5 by 14. So the probability of these two terms, the entropy of these two terms would mean minus 0.64 log to the base 2 0.64 minus 0.36 log to the base 2 0.36. When you evaluate this, you get the number as 0.94. So 0.94 is high entropy or low entropy? High entropy, right?
Right.
Yes, and high entropy basically shows if the system is homogeneous or not. So here the system is not homogeneous, that is, we have a mixed set. And that entropy says the chaos in the system is around 0.94. Okay. The second entropy that we need to calculate is the entropy of the target with an attribute. So let's say we take an example of what is the entropy of playing golf with respect to outlook. Okay. So we saw that playing golf can have two values, yes or no. Yes adds up to 9 values, which is 3 plus 4, 7, 7 plus 2, 9. So 9 yeses and 5 no's. Out of these 9 yeses and 5 no's, we see how many are divided into outlook. Now, outlook is a feature which can take 3 categorical values: sunny, overcast, or rainy. So let's look at yes and sunny. If I go back to my data, yes and sunny. Okay, so probably we can, yeah. So this is, yes, 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 yes. Okay, yes and sunny. So we have 1, 2, 3. Okay.
Sure. Yeah.
Yeah. So we have 3 cases of yes and sunny. Let's say yes and overcast. So we have 1, 2, 3, 4. 4 cases of yes and overcast. And we want yes and rainy. So you just 1 and 2. Right? So 3 cases of sunny, 4 cases of overcast, and 2 cases of rainy. So we go back here and we say, okay, we fill this information here. Along with yes, 3 cases of sunny, 4 cases of overcast, 2 cases of rain. Okay, if we follow the same exercise, we can find for no, there are 2 sunny and 3 rainy. Okay. So what we have done now is we have divided our data with respect to our target class and with respect to an attribute, and we saw how many cases exist for each. So we have 5 cases of sunny. Out of the 5 cases of sunny, 3 belong to playing golf, yes, 2 belong to not playing golf. We have 4 cases of overcast. For the 4 cases of overcast, all the 4 cases of overcast belong to playing golf, yes, and none of them belong to not playing golf. And out of the 5 cases of raining, 2 belong to yes, play golf, 3 belong to not playing golf. Okay. So if, let's say, if I was to tell you that just look at this data and find its entropy. Okay, of the 3 cases, sunny, overcast, and rainy, which case will have the lowest entropy?
Overcast.
Excellent. because out of the 4 examples, all the 4 examples belong to one class. Okay, so this one class is yes. This would be the reason why, if you look at this data, whenever we say from Outlook, we have a case of overcast, we can clearly say yes. We don't have to check after overcast. We don't have to check anything else. We don't have to check other variables, because after overcast we get a pure set, or we get a leaf node. Okay. But here we are trying to evaluate numbers, so this is what we get. Okay, so now we'll say what is the entropy of playing golf with respect to Outlook. So the formula is here. Okay, the entropy of the target with respect to a feature is basically take all the different values for class, and we say probability of that class multiplied by entropy of that class. Okay, probability of that class multiplied by entropy of class. So what is C? C is basically for this attribute, what categories can we take? So for this attribute X, so in this case for the attribute Outlook, we can take categories like sunny, overcast, and rainy. And for each case, for sunny, we'll find the entropy for the target. For overcast, we'll find entropy of the target. For rainy, we'll find entropy of the target. Okay, so let's put things up here. This formula would evaluate to probability of sunny multiplied by the entropy of the target when it is sunny, plus probability of overcast multiplied by entropy of the target for overcast, plus probability of rainy multiplied by entropy of the target for rainy. Okay. So you put here sunny, we get 5, so 5 by 14 multiplied by E32. So E32 is basically entropy 32, which would, we saw how to evaluate this here, which would mean 32 would be 3 by 5, here 3 by 5, 2 by 5, and when we take its this value multiplied by log to the base 2 of the same value, we'll end up with some number. So entropy of 3 comma 2 comes out to be 0.971. Okay, plus probability of overcast, which is 4 by 14 multiplied by entropy of overcast. So since one term is 0 and the other term is 4, that is, it is a homogeneous set, our entropy comes out to be 0. And then we have probability of rainy, which is 5 by 14 plus entropy of 2 comma 3, which comes out to be this value. So you see, entropy of 3 comma 2 and entropy of 2 comma 3 both will end at the same numbers. Basically, it doesn't matter, at least for the entropy formula, it doesn't matter between yes and no. What matters more is how is the distribution. Okay. So when we take both of these numbers and we add it, we get, for playing golf with the attribute Outlook, our entropy looks like 0.693. Okay, so that's good. Then we talk about one more interesting term called as information gain. And information gain basically says that if we follow, okay, information gain is based on the decrease in entropy after a data set is split upon an attribute. So if we are at the decision node, and from that decision node we split based on a given attribute, then what is the information gain that we have got? The information gain that we have got is basically the entropy of the target minus the entropy of the target for that feature. Okay. So again, when we look at an example, this information gain will become a bit more clear. Now we have all the, all the basic steps that will help us to evaluate the decision tree. Decision tree, these are the several steps that we will take. The first step is we calculate the entropy of the target. Next step, the data set is split on different attributes. Okay, so for the target, there are different features. In our case, the features are outlook, windy, humidity, temperature. We'll try to evaluate the entropy for each branch. After the entropy for each branch is calculated, then it is added proportionally to get the total entropy for the split. Okay. Once we have that, the resulting entropy is subtracted from the entropy before the split, which gives us our information gain or decrease in entropy. Doing all these steps will help us to do to split the data set on an attribute. Okay. Once we have information gain, we will choose an attribute with the largest information gain as the decision node, and we will branch based on that. If the branch has entropy 0, that is, if the branch has a leaf node, we will stop there. Otherwise, it will need further splitting. So this further splitting is done recursively on all non-leaf branches till data is split. So we reach to this point which says we need further splitting, which is basically what we did here. Okay, so we will recursively calculate this so that it is easy for us to implement. Generally, tree structures go very well with recursive ideas, recursive implementation. Because if you remember from our class on functions, we talked recursive functions are basically used when my smaller problem is exactly similar to my bigger problem, and that there is a stopping point. As long as these two criteria are there, we can use a recursive function. So here also it is similar. A tree is, the branch is very similar to the tree, and there is a stopping condition. The stopping condition is once we have pure subset. So we'll try to follow this procedure for our data, and we'll see how this can be done. So first step, calculate the entropy of target. So we say play golf, yes or no, 9.5, and we calculate the entropy. Something that we saw earlier. We say that the entropy is 0.94. Okay. Going ahead, now we will split the data for each of the attributes. So we'll find the entropy of playing golf with respect to outlook. We'll find the entropy of playing golf with respect to temperature. We'll find the entropy of playing golf with respect to humidity, and entropy of playing golf with respect to wind. And for each case, we will, as we had done for sunny, overcast, and rainy, we'll divide the data into, with playing golf, if we are looking at temperature and the temperature is hot, there are 2 options. Okay, so 2, mild is 4.2, cold is 3.1. Then playing golf with respect to humidity, it is 3.2 and 4.0. Playing golf with respect to windy, it is 6.2 and 3.3. So in each case, we will evaluate the entropy, and after evaluating the entropy, the 2 entropies, and then after evaluating the 2 entropies, we'll evaluate the gain. So gain for here is 0.247. Gain for here is 0.029. Here gain is 1.152, and here gain is 0.048. Okay. So which one gives us our maximum gain? Outlook. Okay. So Outlook has the highest gain among the others, and since it has the highest gain among the others, I think here I have missed. This is not a representation of the actual data, but maybe ignore this part. If we try to evaluate this, we will have something else. But if we find the highest gain, then this decides, this will be the feature over which we will split. Okay, so as Switcha said earlier, that we will split on based on the most important feature. The most important feature is something that has the highest gain. Okay? Or after splitting, I will get more pure nodes. Okay, and that is the idea. So then we choose the attribute with the largest information gain as the decision node. So here we will choose outlook as the decision node. And once we have outlook in the decision node, we'll say, okay, outlook will become our root node. This outlook can be divided into 3 branches based on the 3 different categories outlook can take: sunny, overcast, or rainy. And for this overcast, we have all yeses. So if I just take a subset of these values, that is here, we have already filtered out that our outlook is overcast. For that overcast, we see what is pending. So we have 3 features more pending: temperature, humidity, and windy. But irrespective of temperature, humidity, or windy, all my options in the output is play golf. Okay, so we don't need to see of any other features. Thus, this becomes a leaf node, and we'll end the node here. Okay, for other things, for sunny and for rainy, we'll have to need further splitting. So we'll go ahead and we'll say, okay, let's look for sunny. So after we have taken outlook as sunny and we filtered out, these are the other 3 features that are pending. If you look at the class, there are 2 values of class, 3 and 2. So we need to further choose which one will work best. Okay. So if you just look at the data, you see for temperature, we have mild and cool. And we have, for mild you have yes, for mild you have yes, for mild you have no. For cool you have yes, for cool you have no. So we can be sure that if you evaluate the entropy of temperature with respect to playing golf, it will be, the information gain will not be very high. because we don't have a clear-cut answer after looking at mild or cool, whether you want to play golf or not. If you look at humidity, we'll see the same structure. We have got high, yes, high, no, normal. We have some examples of yes, we have some examples of no. So again, humidity also has high information gain. But if you look at windy, we see that windy can take either false or true. If I have false, then I can go with simply saying play golf yes. If I have true, I can simply go with play golf no. So then it makes it very clear that windy will be our, if you evaluate the gain, windy will give us the highest information gain. Thus, after sunny, we choose windy as the feature, and then we divide into false or true, and based on this, we get yes or no. Okay, does this make sense? Yes. So for when data is less, it is easy for us to visually verify what decision to take. But just imagine if you have tens of features and thousands of rows, then we would want to have a systematic way of doing this. Okay? And we would use ID3 recursively to be able to solve this. Based on those steps, till we find the root node, we will continue to create the more and more branches and structures of the tree. Once we have the tree structure, what we can do is we can convert this tree structure into series of decision rules. Okay, so we are talking from decision tree to decision rules. So looking at this structure, there can be 5 rules because there are 5 leaf nodes. Okay, 1, 2, 3, 4, 5. For the 5 leaf nodes, there can be 5 rules. Rule 1 is if so we are tracing through each path. Okay, rule 1 would mean if outlook is sunny and windy is false, then output is yes. So that is rule 1. Rule 2 would be if outlook is sunny and windy is true, then value or play golf is no. Rule 3, if outlook is overcast, then we play golf as yes. Rule 4, outlook is rainy, humidity is high, then no. Otherwise, outlook is rainy, humidity is normal, then yes. Okay. So we can simply take decision tree and convert that into decision rules. So what this decision rule can help us for? So when we see unseen data, that is there is new data, and for that new data, if we have to predict something, we just follow through the tree. Either you follow through the tree, or if you have these if-else condition rules, you will follow through the rules and get the answer of playing golf yes or no. Okay, is this fine so far? Okay, do you have any questions on decision trees?
Elijah, if
Yes.
some numbers are involved in our conditions, then decision tree will work out.
Okay, so very good, very relevant question. So in this case, we saw that all of our features are categorical features. Outlook has only 3 values. Windy has only 2 values. Humidity has 2 values. Temperature we did not use in this. Temperature also had 2 values, 3 values, mild, cold, and something. So if instead of that, you have temperature as a feature, and instead of having high, cold, or something, temperature has numbers like 27 degrees to 50 degrees and so on. What we would have to do is we would have to take that temperature and divide that into groups. Okay, and those groups or conditions should mean something like this. If outlook is sunny and temperature is less than 27, then we say yes or no. You understand? Or temperature is greater than 50, we say yes or no. So we will take
But
temperature.
still, how we know less than 27? There will be different. We can categorize differently.
Yes. There can be infinite values between which you could take because that becomes a continuous variable, right? So there can be infinite places where you can split. So there we would again use entropy to decide which is the set point or which is the value that will divide the group maximum. Okay. So you understand the concept of entropy here, right?
Yeah, got it.
Yeah, we will choose that value of temperature, which will be able to give this as a best split. Okay,
Yeah.
so it will depend upon if play golf, we have yes and no here. Let's say temperature, we have 27, 30, 45. This we'll have to take for one number, uh, which is able to divide this into two parts first. Okay, so first we'll look at for what is the number that is able to divide this into two parts. Okay, if we are not able to do it in two parts, then we'll take for number what are the two numbers that divides it into three parts, and so on. Okay, and we'll look for what is the split best here. So let me probably show it using a graph. Let's say that I have temperature on this axis, and let's say this axis. Okay, I just need one axis for this one. Let me. I have a number line for temperature. Okay, and we have data separately on this. Okay, so on this number line, there are different temperatures, and green represents one set of data, and maybe pink represents some set of data. So green says I have a sample here, I have a sample here, a sample here, a sample here. Pink says I have a sample here, a sample here, a sample here, a sample here. Okay, so this is how my temperature is distributed, and some values are yes, some values are no. Okay, so here what I would want to do is I would want to draw a line somewhere which is able to split this best. Okay, what I mean by that is, let's say if I draw a line here, then I say here I have no examples before this line, and after this line, my examples are divided as 4 green and 4 red. Okay, so the entropy of the system is very high. So this line is not a very good line to draw, right? So if I draw a line here, then I look at the entropy. So here the entropy is 0 because I have only one kind of examples here. But on this end, my entropy is 4 and 3, still very high. So my net entropy of the system is still high. Right? I'm looking for what is that one line that I draw that my entropy of the system becomes least. Okay, so probably in this case, I don't have an example like that. One line will not solve my problem. But if I draw two lines, so let's say I draw a line maybe here and then here. So here now I have two lines in which here the entropy is 0. Here and here the entropy is mixed. So my net entropy I'll have some value. Okay. So for a feature like this, for a continuous variable, we would have to analyze what is the lines or how many lines we have to draw so that we can divide the data into purer and purer sets. Okay. This same example with two features would look something like this. So let's say I have temperature here, and let's say I have some measure of humidity, and say humidity is also a continuous value, and I have my data distributed like this. Okay, then we would have to divide this into compartments. Okay, our compartments could look something like this. So let's say we put a compartment here based on temperature. So temperature less than this value, temperature greater than this value, and we have two sets now. It said, okay, now within the set where temperature is less than this value, that is within this set, I will classify based on humidity, this line. So after I put up a line here, now I have a pure subset. So if temperature is less than this number and humidity is less than this number, then say answer as yes. Okay. If temperature is less than this number and humidity is higher than this number, then say answer as no. Similarly, within this group, what I would have to do is, I'll say, okay, but temperature less than this number. Now here, if I draw humidity any line, it will not be able to divide this into two parts, right? I would have to again say, okay, let me put a line here, which says, okay, and then finally a line here. So now each subset is pure. So it says, okay, if temperature is greater than this number and humidity is less than this value, I go here. Okay. So normally the situation is we would, okay, for this case, I would have to, let me undo what I did here. Sorry. In this case, initially only, I would have to divide red into 3 parts. Okay, because I cannot take one feature and then later down again decide based on the same feature. Okay, one feature can be called only once. Okay, so here we will, based on this temperature, we'll divide into 3 parts. Okay. So based on 2 lines, this first line splits it here, second line splits it here. So for both these, we are ending with something called as leaf nodes. If temperature is less than this value, I know my answer should be no. If the temperature is lesser than this value, finally, I know my answer should be yes. Okay. If temperature is less than this value, I have a mixture which can be categorized based on humidity. So if I put a line here, I can say humidity will be this will be. Does that make sense? Okay. So the whole idea is we are looking at features and we are trying to divide that into pure subsets. Okay. Now here I'm doing it manually, but we'll be using the ID3 algorithm to be able to decide what is that value which will be able to divide this in the best case scenario. Okay. And based on that, so maybe for classification, like maybe for continuous feature like this, there will be something more interesting, but we are not looking into that much detail of implementing ID3. Okay, because we would focus on we would not implement ID3. We would simply use scikit-learn's package. Scikit-learn has implemented it very nicely. We don't need to worry about implementing it, but we need to have some idea of why this is working and how this is working. Right? Does this make sense? Do you have any other questions? Okay, so maybe let me ask you some questions. Now we have seen 3 algorithms: KNN, naive Bayes, and decision tree. Out of these 3 algorithms, which will be the fastest to train?
Naive Bayes. No, training will be hard for that. KNN will be less.
Yeah, KNN will take the fastest time to train because there is no training. We're just remembering the data. Yeah. Okay, which will be the fastest to predict?
Decision tree or naive Bayes.
Okay.
Not KNN.
Yeah, definitely. Yes, definitely not KNN. Between naive Bayes and decision tree, can you? Okay, you're saying you don't know. What about you, Srinivas, Richa? Between these 2 guys, can you tell me which will be the fastest to implement or fastest to predict?
I will say decision tree little more.
Yes.
No equations, no calculations.
Yes, true. Here we directly check the value, and from that we just implement if else and we evaluate. For naive Bayes, at least you have to evaluate the term, right? So you have to evaluate. So in this case, you have to evaluate something like this. What is the probability of playing golf? That is, play golf is equal to yes, given the data that we have. Okay, given the data we have. And you also have to evaluate what is the probability of playing golf is equal to no, given the data that we have. And after we get these 2, we will assign some this greater than, lesser than, or equal to. And based on that, we'll be choosing which one to go for, yes or no. Whereas here, we have the rules already defined. Okay. And based on these rules, we can directly say what is the answer. We don't have to evaluate anything. So decision tree would be faster to give the answer. Okay. If my data is having correlation, if the features are correlated, in that case, which one will do better? Naive Bayes or decision trees or KNN?
Naive Bayes.
Okay, that's not right.
Okay.
In fact, when the features are correlated, naive Bayes will do the worst because naive Bayes takes the assumption that they are not correlated. Because of that, we find that formula is mutually expressed, right? We use a formula there, something like this. What is the probability of X given a certain C? And we say this probability is equal to probability of X1 for C multiplied by probability of X2 for C. And that this is our naive assumption. Okay. So when data is correlated, this may not work out. What about decision tree and what about KNN? Okay. So for both KNN and for decision trees, correlation does not play a big role, because we were just looking at the structure of the data, that is the space in which it is divided. And KNN just says that if something is nearer to me or not, based on that, it will decide the label. And here we will divide into space and we'll say within that space. So here also basically we're talking about closeness. How close is my data? And the hope is that all of the data is closely linked to each other or closely spaced into tight spaces. And then this would work out. So we're not looking at correlation in both these cases. Can you tell me a case where decision tree will have a trouble or will have problem?
If something like Fibonacci series or something will come up, which says some kind of series, which we can't group it.
Okay. Okay, so here you see the grouping is happening based on the node, based on the final answer that we're going for. So play golf, yes or no, that is what the grouping is decided on. So at least for now, we are talking about decision tree as a classifier, not as a regressor. So Fibonacci series would not be the target variable, right? Maybe it is a feature. And if it is a feature, we'll have to see how the target variable is associated based on that feature.
If an output is not yes or no, which is not categorical,
That,
it doesn't make sense.
but we have something called a decision tree regressors, okay, which we once we finish classification and go into regression, we may look at this. No, I'm like, at least in the syllabus that I've decided, we are not looking at decision tree regressor. But if you want, we can study and see how regressors will work out. Better regressors are your linear regression, lasso, and rich, and so on. Okay, but decision trees can be used for regression as well. Okay, we have both these options. How it works out will be something else. We'll see how it works out. For even in classification, one problem that I can tell you is, let's say you go to Outlook, you get sunny. You go to windy, you get values. And here you have values for both. With false also, I have true. With false, I have groups of yeses and nos both. Okay. Then you say, okay, then we have exhausted two features already, Outlook and windy. Now we have two more features, humidity and temperature. Let's say you check for humidity also and you check for temperature also. After checking all four features, still I have a mixed set in the end. Do you understand the problem?
Yes, yes, yes.
Okay. So here at every level of the tree, what we are doing is we are taking out one feature out. So after Outlook, we don't need to consider Outlook anymore. At this point, we have three features to choose from: windy, humidity, and temperature. We chose windy, you went down. Okay. After looking at here, let's say we have a mixed set. You have only temperature and humidity to check. You split based on humidity, then you split based on temperature. Even after splitting based on temperature, you have a mixed set of yeses and nos. Okay. Then we are stuck, because what this basically means is, even after considering all the dimensions of data, the smallest subset is still mixed in nature. Then what we do in those cases is you would take still the majority. So let's say you have three yeses and two nos. We will define that leaf node as yes. Okay. So it again depends on my data. If my data is, so here we come to another problem called as linear separability of the data. If my data is not linearly separable, okay, then decision trees will have a big problem. Okay. So if my data is linearly separable means I am drawing these lines, and based on these lines, I can separate the data or not. Sometimes it will be, it will be a very complicated situation. Like you have a feature here, let's say temperature and humidity, and your data looks something like this. Okay. So now this is very difficult to linearly separate. Okay. Here, in fact, what you need is a circular space that can separate this. Okay, you will say anything inside the circle is one thing, anything outside the circle is another. So you are talking about a non-linear separation, rather than this one. So their decision trees will face some trouble. Does that make sense?
Yep.
Okay. Yes, so I think we have covered most parts of decision tree. If you have any questions, we can take that, or we'll move to a very quick part. Let me go here. Something called as random forest. So I'm just clubbing this together because these algorithms are very, very close to each other. Okay. So random forest is basically if you take multiple trees and you attach that for making decision, we get to something called as random forest. Okay. Can you tell me what will be the advantage of this method? Okay. Any guesses? So random forest is again another classifier, and it uses multiple trees to be able to make the prediction. So okay, let me make it more simpler. The idea is very simple, that we say there is wisdom in the decision of a crowd. Okay, if there is one person making judgment, then that 1% may or may not be right. Okay, or the judgment of that one person depends only upon the experiences of that person. But let's say there is a panel of 10 people, and 10 people are making judgments, and we can take the collective experience and we can take all of their verdicts, and based on the net verdict we can make a decision. So that is a better decision than just one person deciding. Make sense?
Yes.
Okay, so here in random forest, what we do is we create multiple trees, and we will take the output of each tree, and we'll say, let's say we create a random forest with 10 trees. 7 trees are saying go play golf. 3 trees are saying don't play golf. We will believe in yes. That is our net. Our majority is saying go play golf. So the thing here is all the trees should be different. Okay. If all trees give the same answer, if all trees are exactly the same, then there is no point in having a random forest, right? So the question is, how can we ensure that different trees give us different outputs? Or how can we ensure that there is, what do you say, there is variation between the trees? So one way of doing that, so here there are basically two ways of ensuring that the trees give different outputs. One is called as bagging, the other is called as feature randomness. Okay. So what is bagging? Bagging basically means that I will train my data. So my training data for making the trees will be selected randomly in a bagged fashion. Okay. So what does that mean? Let me show you. Let's say I have 10 training examples. 1, 2, 3, or let's say I have 6 training examples. And what with decision tree, what we'll do is we will give all of this data to train a model. Okay. So with random forest, what we'll do is, let's say we are going with tree 1. Tree 1, we will take one data. So we'll take one data, and then we will take another data from this set, and let's say we are not removing one out of the picture, so that the tree can take one again. So let's say it takes 2. After that, it chooses again, it takes 2 again. It chooses again, it takes 3. It chooses again, it takes 1. It chooses again, it takes 5. So we have 1, 2, 3. So now here also we are training with 5 samples, but in that 5 samples, effectively we are just training with 4 samples. They are 1, 2, 3, and 5. Does that make sense? So we are training with a subset of your main data to this model, and this subset is chosen by bagging the elements, by bagging the samples. Okay, bagging the samples basically means that I will choose one, add it to my set, then I choose another one, but I'm allowed to take the first one as well. So what will happen is you will end up with some of the data not going to the model. So in this case, samples 4 and 6 are not going to train this tree. So when this happens, my tree T1 will create a different kind of a structure. It will not be the same decision tree like the first case. Okay. So like this, I have tree 1, I will have tree 2, I'll make tree 3 and so on. And at the end, I will have, say, let's say 10 trees. Okay. These 10 trees will have different structures. And their different structure depends upon what sample they have chosen. Okay. And depending upon what sample they have chosen, we will have a different tree structure that will ensure that there is variation between the data. Does that make sense? Okay. So that is how we can create a variation using bagging. The other case is we can use variation, or how we can create variation is by something called as feature randomness. So feature randomness is, we saw that once we choose a root feature, we can go down and we can choose, okay, Outlook can take three options: sunny, overcast, and rainy. For sunny, we have to then see what features can we take. So here we are left with three features. We are left with humidity, temperature, and windy. So feature randomness is, let's say for this case, we will not allow humidity as an input. We will only allow these two, temperature and windy, and we are doing this randomly. So sunny, after this point, my algorithm is forced to either choose temperature or windy. It cannot choose humidity. So that is another way of creating some variation in the data. Okay. And the idea is this, that once I have different trees, all the net trees will try to capture the essence of the data. And I'm not going for very specific values. Okay. So random forest, I don't know if you have heard this term before, which is just after once we finish our classification, we'll talk about these terms. Have you heard of something called as overfitting? Overfitting, underfitting, and maybe normal or the right kind of fitting. Have you heard of these terms before?
Yes.
Okay. So maybe even if we don't fully understand what these terms mean, I would want to say that random forest will prevent overfitting. It will prevent overfitting of the data. Okay. And this is a very important feature. Decision tree does not have any, or decision tree, we can do something where decision trees can also prevent overfitting. But the way random forest is made, it inherently captures the idea that it will not overfit. I will not use all of the data to train the model. I'm using a subset of the data to train the model. I'm using feature randomness to train the models. So each of the models will not learn too much from the training data. They will learn the essence or the nominal behavior from the training data, which can be used for further prediction. Okay. So probably next class, we can start our discussion with what these values are. I hope random forest is clear so far. If you have any questions, we can discuss this, else we will end the class now. Okay, yeah, great. So, yeah, we have overfitting, underfitting is not a very huge topic. So we'll discuss that in next class. And we'll continue with our Titanic dataset, where we finished Titanic dataset with feature engineering. We had all the pre-processed data. Now we will try to implement some machine learning algorithms on that data, and we'll see how good or bad they're doing. Okay. Okay, then I'll stop recording.